PRYSTINE Supply Chain 7 presentation of Demonstrator 7.3. Positioning of this demonstrator. It is about autonomous control to study AI-based decision-making algorithms for highly automated vehicles in highway and urban scenarios, considering a traffic state prediction network V2X. This is an overview of the hardware and software architecture. Let's take a look at the input of the different partners. First, TUE, Eindhoven University of Technology. TU Eindhoven provided the car, camera system, computing hardware and data acquisition system. Then partner NXP. NXP provided the front and rear radars. Partner Innoluce. Innoluce provided the forward-facing LiDARs. The partners NEY and DAT Mobility, supported by Mobility Moves. NEY provided the communication setup between the cloud and the vehicle, and DAT Mobility, supported by Mobility Moves, provided real-time traffic state prediction as a virtual external sensor outside the vehicle. And finally, partner TNO. TNO provided the hybrid AI setup for the decision-making system. What is Demonstrator 7.3 about? For autonomous control, the required software becomes too complex to be written by hand. Therefore, we have researched if this can be solved by using artificial intelligence, AI, for decision-making tasks. AI algorithms learn from the driving behavior of a human driver. Demonstrator 7.3 has been driving around to collect data for training the AI algorithm. The car was fully equipped with sensors such as LiDAR, radar, cameras, and a cloud connection for receiving the traffic state prediction. The car has driven multiple weeks on specific routes on the highway and in urban setting. The collected data of the sensors was processed and used for training the AI algorithms. What is Demonstrator 7.3 about? We learned over the last years in PRYSTINE that extracting human driving behavior from collected data is mathematically very complex due to the limited amount of data which we had collected and the computational power required for inverse reinforcement learning, called IRL. Therefore, TNO has chosen to model the human driving behavior by hand in order to continue the research. The decision-making process is composed of a hybrid AI system combining a knowledge graph, called Grakken, with a Monte Carlo tree search algorithm. The predicted traffic state is an example of the use of domain knowledge in Grakken. The use cases in our research. We focused on 3 highway use cases and 3 urban use cases. 3 use cases are selected to be shown in this Demonstrator 7.3 movie. The autonomous lane change, the autonomous lane change with traffic state prediction, and a cyclist coming from the right in urban setting. First use case, the autonomous lane change on the highway. The red car, called Ego, is driving faster than the green car in front of it, called Target. Since there is no upcoming traffic from behind, the red Ego will decide to overtake the Target. Now we first start with data collection on the highway. We drove on the highway in the same setting as the scenario. And while driving, we recorded the data of how the human driver acts in this scenario. Then we started training the AI algorithm. The collected data is then used for training the AI algorithm. After that, we will run the AI algorithm. When we then run the AI algorithm for decision making, the AI system will provide the best possible action which it has learned from the data of the human driver. The outcome of the AI-based decision maker. First, let's take a look at the axis. Horizontal shows the relative distance between the cars. Vertical shows the possible actions found by the AI algorithm in the collected data. In other words, the actions that the human driver had performed. Each blue dot represents the action that the AI algorithm gave as output when running the AI-based decision maker at different relative distances. The outcome of the AI-based decision maker. In our data collection, the human driver usually overtakes, latest, at a distance between 30 and 27 meters when driving at highway speeds. Therefore, we focus on the actions which the decision maker proposed at that relative distance. And as you can see, no unsafe actions, such as hard acceleration, are proposed at this relative distance. And as you can see, at this relative distance, the action to keep speed and go left, overtaking, is the most consistent action which the decision maker proposes. In the simulation environment Carla, this is visualized as you will see in the next movie. The outcome of the decision maker is visualized here. The red ego overtakes the green target because it's safe. The second use case in this presentation, autonomous lane change with traffic state prediction. In the second highway use case, again the red ego is driving faster than the target in front of it. However, in this case, the traffic state prediction is communicated to the car. The Graken knowledge base takes this knowledge into account. Since the car will have to stop anyway for the traffic jam, it has no point to take over. The traffic state prediction functions as an external, additional sensor to the car, which input is used by the decision maker. The traffic state prediction provides a complete and consistent traffic view for the area. In the map, the colors and the bandwidth show the predicted speeds and flows. The system already knows the traffic situation ahead of the ego vehicle. And now the ego vehicle enters the traffic queue, which was already foreseen. Again, the red ego vehicle drives faster than the green target, but due to the known traffic state prediction, it decides to not overtake because it will stop anyway. Third use case, cyclist coming from the right. In this urban scenario, the red ego vehicle approaches a crossing while a cyclist is coming from the right. The ego vehicle will have to stop for the bicycle. The outcome of the AI-based decision maker. Again, the horizontal axis shows the relative distance between the car and the cyclist. The vertical axis shows the two proposed actions derived from the human behavior. A human driver usually decides to take action at a distance between 25 and 17 meters when driving at a low speed. Therefore, we focus on the actions which the decision maker proposed at that relative distance. As you can see, no unsafe actions are proposed. At this relative distance, the actions of low, soft braking is the most consistent action which the decision maker is proposing. This is safe behavior as a human would do. Also here you see the outcome of the decision maker visualized in Carla. Demonstrator 7.3 Conclusions based on the results of the PRYSTINE project. Conclusion 1. Learning from human driver's data, assuming that the driver only performed safe actions, allows the AI-based decision maker to discard unsafe or undesired actions. For example, the human driver never accelerated in the urban use case, so the AI decision maker never took that action into account, meaning that it actually never proposed an action which it had not seen in the training data. More research is needed, but the approach seems very promising. Conclusion number 2. The hybrid AI approach supports the AI-based decision maker by taking the context and domain knowledge into account. For example, if the traffic state ahead is known, actions which include this knowledge can be chosen, resulting in a better set of possible actions. A hybrid AI system can be trained in shorter time with less data, and the resulting behavior is safer. Conclusion number 3. The choice for IRL, inverse reinforcement learning, as AI approach was a novel choice for decision making. In this project, we have found that in principle it is not only possible but also a promising direction. However, more research and development would be needed for real-life implementation. Thank you very much for your attention on behalf of all the partners of Demonstrator 7.3.